Hello everyone, I am Li Qina from the Electronics and Information Engineering Teaching and Research section at Wuzhou University and welcome you to this mini lecture. Today we'll cover section 6.1, the Laplace transform of continuous time signals. From earlier chapters, we've learned that the Fourier transform provides a way to map signals from the time domain to the frequency domain, allowing us to better understand their characteristics from a frequency perspective. However, some signals do not satisfy the conditions of absolute integrability or summability, and thus their Fourier transform does not exist. In these cases, we cannot directly use frequency domain analysis to study their properties. To address this issue, we introduce complex frequency domain analysis of signals, namely, the Laplace transform of continuous time signals. Next, we will approach this lesson through three main topics. First, let's derive how the Fourier transform extends to the Laplace transform. Some common signals do not have a Fourier transform because they are not absolutely integrable or summable, such as the exponentially growing signal ft equals e to the alpha t times ut, alpha greater than 0. If we multiply this exponentially growing signal by a decay factor e to the minus alpha t, then when sigma is greater than alpha, the signal becomes exponentially decaying. In this case, the Fourier transform exists, and the expression can be written as follows. Now, generalizing this approach gives the following formula. By letting S equals sigma plus j omega, we obtain the Laplace transform formula as follows. This shows that taking the Fourier transform of a signal ft multiplied by the decay factor e to the minus alpha t is equivalent to taking the Laplace transform of ft. Here, the complex frequency S equals sigma plus j omega, where sigma is the real part and j omega is the imaginary part. Taking the inverse Fourier transform of a signal ft multiplied by the decay factor e to the minus alpha t leads to the following formula for the inverse Laplace transform. The symbols for the Laplace transform and its inverse are often written as follows. From the inverse Laplace transform, we can see its physical meaning. A signal ft can be represented as a linear combination of complex exponentials e to the st. Fs gives the composite amplitude of harmonics per unit bandwidth and can be viewed as a density function. S is called the complex frequency, and Fs is known as the complex spectrum. In practical engineering, signals are generally causal, with the time variable t ranging from 0 to positive infinity. This naturally leads to the use of a one-sided Laplace transform and its inverse, with the corresponding formulas given as follows. In the one-sided Laplace transform, the lower limit of the integral is defined as 0 negative, which represents the initial state of the system before any input signal is applied. This definition is mainly intended to handle impulse signals occurring at t equals 0, as well as the zero input response of a system analyzed in the S domain. If no impulse or its derivatives exist at t equals 0, the lower limit of the integral can be simply taken as 0. Since the absolute integrability of a continuous signal is a sufficient condition for the existence of its Fourier transform, multiplying the signal ft by a decay factor e to the minus sigma t before taking the Fourier transform is essentially equivalent to computing the Laplace transform of ft. From this, the sufficient condition for the existence of a one-sided Laplace transform can be derived as shown in the following expression. That is, the signal ft multiplied by the decay factor e to the minus sigma t satisfies the condition of absolute integrability for any unilateral signal ft. If the signal ft multiplied by the decay factor e to the minus sigma t satisfies the condition of absolute integrability, ft itself also satisfies the following condition. In other words, when the signal ft is multiplied by the decay factor e to the minus sigma t, its limit approaches 0 as t tends to infinity. The range of sigma values that makes the above two conditions valid defines the region of convergence, ROC, of the Laplace transform. For example, In the expression above, this corresponds to sigma greater than sigma 0. For the case where sigma is greater than sigma 0, the region of convergence, ROC, in the S-plane is shown in the figure. The horizontal axis represents the real axis sigma, while the vertical axis represents the imaginary axis g omega. The line sigma equals sigma 0 is called the axis of convergence. The point sigma 0 is referred to as the absolute convergence coordinate, and the condition sigma greater than sigma 0 defines the ROC. Thus, the ROC is determined with respect to the real part sigma in the S domain. In the following example, we are asked to determine the ROC for the Laplace transforms of 5 different signals. To establish whether the Laplace transform exists, we primarily examine the range of sigma values for which the signal ft multiplied by the decay factor e to the minus sigma t either satisfies the condition of absolute integrability or approaches 0 as t tends to positive infinity. Accordingly, the ROC for the Laplace transforms of the 5 signals are derived as shown below. Based on the example problems, we can summarize the ROC for the Laplace transforms of several common types of signals. 1. Finite duration energy signals with non-zero values over a limited interval, such as a rectangular pulse. Their ROC is the entire S-plane. 2. Constant amplitude signals or oscillatory signals of constant amplitude, such as the step function or a sinusoid. Their ROC is the right half of the S-plane. 3. Polynomially growing signals proportional to positive powers of t, such as t to the n. Their ROC is also the right half of the S-plane. 4. Exponential signals e to the at times ut. Their ROC is the half-plane sigma greater than a. 5. Non-exponential order functions such as t to the t. Their one-sided Laplace transform does not exist. Now let's derive the unilateral Laplace transforms of some commonly used signals. The first one is the common unilateral exponential signal e to the lambda t times ut. Substituting this into the definition of the unilateral Laplace transform, we obtain 1 over s minus lambda, ROC, sigma greater than lambda. Similarly, for the unilateral exponential signal e to the minus lambda t times ut, the transform is 1 over s plus lambda, ROC, sigma greater than minus lambda. In the same way, the unilateral Laplace transforms of purely imaginary exponentials and complex exponentials can be derived, with results expressed as follows. The second type of signal is the sinusoidal signal. According to Euler's formula, a sinusoidal signal can be expressed in terms of complex exponentials, and we have already derived the one-sided Laplace transform for such exponentials. Based on this, the one-sided Laplace transforms of cosine omega 0 t times ut and sine omega 0 t times ut are given by the following formulas. The third type of signal is the step signal. Earlier, we derived that the one-sided Laplace transform of the exponential signal e to the lambda t times ut is 1 over s minus lambda. For the one-sided exponential signal, if we take the limit as lambda approaches 0, we obtain the step signal. Correspondingly, its Laplace transform 1 over s minus lambda tends to 1 over s as lambda approaches 0. Therefore, the one-sided Laplace transform of a step signal is 1 over s, with the region of convergence sigma greater than 0. The fourth type of signal is the impulse signal. Substituting the impulse signal into the one-sided Laplace transform formula and applying its sampling property, the result is obtained as 1 with a region of convergence over the entire S-plane. Similarly, the one-sided Laplace transform of the impulse pair signal is s, also valid over the entire S-plane. Extending this further, the one-sided Laplace transform of the nth derivative of the impulse signal is s to the n, with a region of convergence covering the entire S-plane. The fifth type of signal is a positive power function t to the n times ut, where n is a positive integer. Substituting t to the n times ut into the unilateral Laplace transform formula, and applying integration by parts from advanced calculus, we obtain the Laplace transform of t to the n times ut equals n over s times the one-sided Laplace transform of t to the n minus 1. Following this reasoning, the unilateral Laplace transform of t to the n times ut is n factorial over s to the n plus 1. ROC, sigma greater than 0. As a special case, the ramp signal tut has the unilateral Laplace transform 1 over s squared. ROC, sigma greater than 0. The Laplace transform we studied today serves as a mathematical bridge in communication systems, converting complex time domain analysis into simpler operations in the complex frequency domain. It plays a crucial role in signal analysis, system design, stability verification, and circuit optimization. Please reflect on today's lecture and complete the following homework exercises to consolidate the concepts learned and deepen your understanding. That concludes today's mini lecture. See you next time.